well, to make the low angular momentum states of the outer electron, right? I mean, I've shown these two. You can also get 6s and P. With a little work, you can get to 6s and G and 6s and F. It's not at all obvious that you can get to the higher angular momentum states. Because for each of these, to get to another angular momentum here sort of means another laser. Okay. So how could you, in fact, make these? Okay. So this was actually suggested by Dan Kleppner a long time ago. And basically, it's do field ionization backwards. Okay. So if you excite barium in an electric field, let's say 1,000 volts per centimeter, and this paper is taken from the Amica Tom work on Laurence Prouvost and Pierre Pillet and Pierre Camus. But if I can excite with a second laser any one of these Stark states of barium, bound Stark states. So this would be 6s, and they chose N of 13. And when you, in fact, go back to calculate the energy levels going back to zero field, each of these Stark states goes back into one angular momentum state. And so if you go back slowly enough, you can adiabatically pass from a Stark state into whichever angular momentum state you like by just choosing the Stark state appropriately. I should point out also that you can do this in alkaline earth atoms because the zero field levels are far apart because the polarizability of the core is much bigger than an alkali. I don't think you can do this with an alkali. Okay, but anyway, so the experiment of probing high angular momentum autoionizing states is done by making these bound states of high angular momentum and then once again exposing them to the light to drive the core transition. Okay, so with these two laser pulses come during the presence of an electric field, you turn it off, then you send in this laser, and then you collect the ions. Okay? So these are the Amica Tom data in which they drove transitions from the 6s13L states of 5 up to 12 to the 6p 1/2 13L states, these, and 6p 3/2. And of course, the p 3/2 state of the ion has angular momentum 3/2. It in fact supports a quadrupole moment, and you get the typical quadrupole pattern. Now, of course, implicit in these spectra is you could maybe believe that these are getting narrower, but actually they were measured by Bob Jones in his PhD thesis, and these are in fact the scale decay rates as a function of angular momentum for n equal 12 in barium. So a scale decay rate of 1 means that it's ionizing, it ionizes with 100% probability in one orbit. And so by the time I'm out to this point, I have 10 to the minus 4 probability of ionizing on any given orbit. And so in these states, in this region, you can simply scan that last laser, measure how wide it is, and everything is fine. I should point out, unlike the lasers we've been hearing about lately, these are not 10 kilohertz wide lasers. These are more likely to be 30 gigahertz wide lasers. And when you get to this point, actually these widths are well below the line width of the laser. And Cook suggested something that's truly brilliant, which is that the widths are intrinsic, so the profiles of autoionizing states are intrinsically Lorentzians that have long wings. And so if you go way out in the wings, you can actually, where you have zero spectral resolution, you can actually still figure out how wide the Lorentzian is. And so that technique was used to measure these. Now, the other thing that's interesting is by the time at n equal 12, by the time you get out to L equal 9 or 10, the autoionization rate is actually less than the radiative decay rate. So if I make one of these states that say 6p 12, L equals 10, it does not autoionize. It just decays. The inner electron just radiates the photon away. Oops. Okay. So if you don't want to be switching, okay, let me back up 2 slides. Well, sorry. In the previous Stark switching experiments, basically the electric fields were about 1 kilovolt per centimeter. So a microwave switching technique was discovered by Schumann. Actually, Frederick Merck may have done this too. I'm not sure. But if you use microwaves, actually, instead of your 10 gigahertz wide laser, you then no longer have to have, and start from a Rydberg state, you don't have to have this kilovolt per centimeter field. You can use fields of less than 10 volts per centimeter. With the laser, make this state, drive it to any one of these, and you no longer have this kilovolt field problem to mess around with. Okay, anyway, let's go on to the isolated core excitation again. So I essentially claimed that what's happening when I drive this transition is that the barium plus is making a transition and the outer electron is just sitting there watching. Okay, so I would like to make this notion a little bit more quantitative. In fact, you can make that more quantitative. And I would like to motivate it by considering what happens to this spectrum if I simply raise the power in this laser. So actually, I should point out, to obtain this spectrum required lots of neutral density filters. Okay, so if you raise the power, that previous spectrum would be a little narrow peak in here. You see something that looks like this. Okay, which sort of looks like the interference patterns that we had previously, but it's not interference. And but there are several notable features here. It's kind of flat on the top. But this is where 6p15d is right here. And this is clearly the energy of 14, 13, 16, 17, and so on. And these are, again, these two photon coincidences. So this looks for all the world like it's interference, but it's not. It's you can, and I will now show you how you can calculate this spectrum that looks pretty much like what I just showed you. So let's just go back to my original claim. The spectrum is due to the ion transition with a spectator electron. Okay.